let's design distributed logging system. Now I know that most of you watching this might be wondering, this sounds like one of those boring designs, right? Something that will never come in the interviews. But actually, this is one of the most important systems out there. Now, if you have ever worked as a software engineer, you know that at least 50% of your time just goes into looking at those dashboards, alerts, and monitors. When you're on call, these dashboards are your best friends and sometimes enemies too. They are what tell you when something's going wrong, where it's happening, and how bad it is. And that's exactly why distributed logging system is critical, because it's the backbone behind all of that observability magic that's happening. Just imagine how far we have come. Let's go back 10 or 15 years ago. Logs were always scattered between these different servers, different machines. If something would have gone wrong, you would have to manually go into these multiple servers, pull out those log files, and try to understand what went wrong. If it sounds messy, it is. It is a lot of work, it is time consuming, and it's painful for the developers. Now imagine this, you are working on modern microservices based architecture. There's microservice 1 handling authentication, microservice 2 handling the payments, and then there's microservice 3 managing the notifications. Each of them running on separate servers or clusters, generating their own log files. Suddenly, a user reports an issue. You start digging into the logs, but guess what? These logs are scattered everywhere. Different servers, different formats, somewhere JSON, somewhere XML, somewhere plain text, different timestamps. You end up feeling like this developer in the picture saying, I can't make sense out of these logs. It's so confusing to me. And this is exactly what used to happen 10-15 years ago. And now we don't see that because of centralized logging system. And that is why we are learning this design. So formally speaking, we have three big problems here. The first one is slow debugging. You have to manually log into multiple machines and search for errors. The second one is lack of visibility. It's hard to get a complete view of your system's health and performance. Maybe some of the servers are getting most of the traffic, or maybe one of the servers has gone down. You don't know the overall health. The third one is inconsistent logging. So different services log services in different formats. So it's difficult to connect the dots between the related events. So for example, let's say somewhere it's a JSON format, somewhere it's a XML, somewhere it's a plain text. And in order to make sense of all of those inconsistent logging, it gets little messy there. So to solve this, we build a distributed logging system. This is a centralized system that collects logs from all of these microservices into one place. You can visualize everything on beautiful dashboards using tools like Grafana, Kibana, or even OpenSearch dashboards. You can search across millions of log lines instantly, monitor errors in real time, and even trace issues across different services. These are some magical and so powerful tools, and when you're working with them, you do not appreciate these systems much. But when I delved into this system, I was like, this has solved such a big problem, and I wasn't appreciating it much. So now, let's take a moment to understand the distributed logging system and why they are such a key part of every large-scale architecture. Let's begin the design. Now that we understand why distributed logging systems are so important, let's talk about what they actually need to do. Let's now move on to the requirements section. In here, let's first discuss about the functional requirements. At a high level, these are the key things our logging system must handle to be useful in the real world. The first one is the obvious one, which is unified log collection. The first and most important requirement. The system should collect logs from all application services and environments into one central place. We don't want logs scattered around hundreds of servers. Instead, everything should flow into a single unified pipeline, whether it's coming from your authentication service, your payment service, or your recommendation service. This centralization is what makes debugging and analysis even possible in large distributed systems. Okay, we are done with the obvious one. Let's now move on to the second one, which is efficient search and retrieval. So once all the logs are in a centralized place, we also need the capability to search them efficiently. Developers should be able to query logs by keywords, timestamps, or even service name. That's a very common use case. So, for example, you might want to search for every request where the response time was more than 2 seconds, or every log entry with timeout error being mentioned there in the last 10 minutes or even an hour. So, those are some examples. One very important example I want to mention here is tracing a single request. This is the most common use case where we ask it to trace a single request starting from, let's say, the authentication service onto multiple services onto the database. That's what we call end-to-end request tracing. That gives us the whole picture on what happened with a particular request. A very important one. Now let's move on to the third one is distributed storage. So logs are huge in volume, especially in large scale systems that generate millions of entries per minute. So we can't just dump them into a single database. That would be absurd. We need distributed storage, something that's reliable, scalable, and fault tolerant. And we have a popular choice for that. We'll look into that when we are doing the high level design. But the meaning is that if one of the node fails, your logs are still safe and accessible. The fourth one is centralized visualization and monitoring. Now, collecting logs is great, but developers don't want to read plain text all day. We need a dashboard, a centralized visualization tool like Kibana, Grafana, or OpenSearch dashboard where people can look and visualize what's happening. This is where engineers can see everything like graphs or error rates or monitors and make sense out of what's going on. We also see some alerts being set up that notify us when something unusual happens. And the last one is log retention. So log retention is very, very important. I know logs can't be kept forever. That would cost a fortune, and that doesn't make sense too in some cases. We want to have a system that can retain logs for a certain period of time, maybe 7 days or 30 days, and then they can basically purge or archive them for cheaper storage. This is not just for saving space but also meeting compliance and privacy requirements. So, to summarize, our distributed logging system needs to collect, store, search, visualize, and retain logs efficiently. If any of these pieces go missing, you end up with a half working system that's painful to debug. We want all of these things. Now that we have covered what the system should do, let's talk about how well it should do it, the non-functional requirements. These are not about the features, but about the quality of the system, speed, scalability, availability, reliability, and security. So let's go through some of the important ones here. So the first one is low latency and minimally intrusive. Now what does this mean? So the first rule of logging is don't slow down the application. Logging should happen quietly in the background without affecting user-facing performance. So when a request is being processed, it shouldn't be waiting for the logging system to finish writing data. That's why log ingestion is usually asynchronous. Logs are shipped off to the logging pipeline without blocking the main flow. And that is why we aim for low latencies. So the log ingestion, ideally in our case, we are assuming the P95 should be within 25 milliseconds, and the log search for that P95 should be within 100 milliseconds. So that means even under heavy load, 95% of log requests should complete within those limits. Now moving on to the second one, which is high scalability. So a good logging system should scale horizontally, meaning we can simply add more machines when the log volume increases. In large organizations, the scale can get massive. We might be ingesting 300,000 logs per second, storing 5 terabytes of new data every single day, and even more. We also might see that we need 200 search queries per second on the dashboard, and each of those queries are pretty heavy. So scale is very important. So all in all, we'll assume that the scale that we want to reach is the ingestion rate should be around 300,000 logs per second. The hot storage that we talked about should be around 5 terabytes per day, and the search load is around 200 queries per second. Now the third one, high availability and reliability. Logs are often your only source of truth during outages. So your logging system must be highly available and obviously much more reliable than your actual system. Even if one part of your pipeline goes down, the system should still continue accepting and store logs without data loss. There should not be any single point of failure, and storage must be durable. And we want that logs are never lost unless we delete them after a certain period of time. So, a good target here would be to get an end to end availability of around 99.999%. Now, the last one, which is security. In many of the cases, logs contain very sensitive data. These can be sometimes API keys, user IDs, or even personal data. So the system needs strict access control. Only authorized users should be able to view and query those logs. Developers should avoid logging sensitive information like passwords or credit card numbers in the first place. That's obvious. But in some of the cases, there can still be things, for example, user IDs that's still present there. And we do not want it to get leaked in any manner. So, in summary, we should ensure proper access control and data handling for those logs. We might end up using some encryption here and there. I know I'm getting a little bit into the high level design, but I'll stop it here. So, these are the four very important non functional requirements. There can be more, but in this design, we'll be focusing on these four. Now let's move on to the high-level design of our distributed logging system. Let's see how everything connects, from user making a request all the way to the logs being collected, processed, and stored safely. So here's the first step. The client is making a request. Let's say the client makes a request, maybe a login request or payment request to the system. The API gateway is the first entry point. When the gateway receives the request, it generates something called as correlation ID, a small but very important concept. Let's understand this in a simple manner now. This correlation ID, you can assume it as a unique tag that gets attached to the request and travels with it through all of the microservices involved. So it's basically like a unique ID for the request. So whether the request goes through one service or 10, every log produced along the way carries that same ID. So if you want to keep track of what happened to this request, which all services did it go, you can use this ID. Let's say something goes wrong. You want to keep track of that log. You can just track that one request across multiple services just by searching for its correlation ID. It's like giving every request its own fingerprint. Now let's move on to the second step where we'll see collecting logs on each service. So once the request hits the backend services, say microservice 1, microservice 2, microservice 3, each of them starts writing logs locally. These logs might include info messages, errors, debug statements, basically everything that helps us understand what's happening inside the system. So here's the challenge. Until now, these logs are stored across multiple servers. So we need to collect them efficiently. And for that, we use something called as daemon set log agent. Now this seems very complicated, but it isn't. Think of daemon set log agent as a little sidekick running on every server, continuously watching log files, picking up new entries and forwarding them downstream. It basically runs on the side so that it doesn't disturb the request handling. Some of the popular choices for this are FileBeat and FluentBit. They are lightweight, efficient tools designed to collect logs for many machines at once. The task for FileBeat or FluentBit is not only to transfer the logs downstream, there are few more things that it does. This daemon set agent also attaches metadata like service name, timestamp, and even masks sensitive data like passwords before forwarding. Obviously, you won't have passwords in the logs, but let's say you have some API keys here and there, so it basically masks all of that. Ideally, you shouldn't log that too, but let's say somebody does that, or some other sensitive information is there. So it does the purpose of masking. So now we have our logs being collected automatically from every service in real time by these agents. Note that in the previous diagram, we never showed relation between these microservices, but they actually communicate with each other and produce their own logs, as we can see in this diagram. Here, as you can see, microservice 1 is chatting with microservice 2 and 3, and it has its own database and whatnot. But in the previous diagram, we never showed that because we are focused on the distributed logging design. All these log agents that you see here send the logs to Kafka. the heart of our logging pipeline. Kafka is a distributed message queue, and its job here is to safely store and manage the massive flood of incoming logs. You can think of Kafka as a high speed mailroom of your system. Every log message that you see here gets dropped off, categorized, and stored until someone comes and picks it up from there. So let's break it down. What Kafka does. Kafka, first of all, organizes the logs into topics. You can understand it like folders, and each topic is further subdivided into partitions to handle very high volumes. Secondly, each log entry includes useful fields like timestamp, service name, correlation ID that we saw earlier, log level, and message. And third thing to know is every new log that you see is added to the end with something called as offset. Basically, the position of that log inside the partition. Now, this design makes it super easy to replay messages later if needed or to recover from failures. The coolest part here is consumers like Apache Flink or other storage systems can read these logs from Kafka at their own pace. They don't need to rush anywhere. They track offsets so even if they restart, they know exactly where they left off. Kafka essentially acts as a buffer, decoupling log producers from the consumers. Here, producers are those daemon agents, and the consumer is Apache Flink. It helps absorb spikes and ensures that logs are never lost, even during heavy loads. And that's why Kafka is such a popular choice. It provides durability, reliability, and smooth handling of huge volumes of logs. So let's summarize what we have seen until now. Requests start at the API gateway, which assigns a correlation ID, an ID that is given to a request so that we can track it easily. Then, microservices generate these logs locally. Log agents or daemon agents collect and forward them to Kafka. And finally, Kafka buffers everything reliably for downstream consumers. So now our logs have safely landed in Kafka. The next step is to actually do something useful with them, and that's where Flink comes in. Think of Kafka as the giant mailbox holding all of our logs, and Flink as a super efficient mail sorting machine that organizes everything, filters junk, enriches data, and sends each mail to the right destination. Sounds complicated? Let me simplify that for you. So Apache Flink's job is to do the following. The first one is parsing and validation. Flink grabs logs straight from Kafka. If logs are raw text, Flink parses them and turns them into structured records, usually JSON or something similar. And if logs are already structured, like JSON or Protobuf, Flink simply validates them to make sure the schema matches. This step ensures clean and consistent logs down the pipeline. So that is parsing and validation of the schema. The second step is enrichment. Flink enriches logs with some extra context. This could be things like region or data center name, Kubernetes pod or container labels, application version, instance ID, and more like that. Basically, Flink adds metadata to make each log more meaningful and useful when analyzing later. So instead of just seeing timeout error, you usually see there as timeout error came from service A in region X, version V2, pod Y. Much better, right? Much easier to debug. Now, the third thing that it does is filtering. Now, this is very important. Flink filters out unnecessary noise. For example, debug logs in production doesn't make sense, right? So it just filters them out. We don't need millions of those debug logs. They'll just burn money and storage. So Flink just drops those low value logs. Maybe keep only 1% of that repetitive info logs and make sure to keep those errors and warnings. This reduces cost and keeps only actionable signal. The fourth step is aggregation. Flink can also aggregate logs in real time using windowing techniques, sliding windows, tumbling windows, etc. Now, what does that mean? Instead of storing every single raw log, Flink can compute metrics like error rate per minute, average latency for the last 5 minutes, top 10 most common error codes, basically turning raw logs into real-time metrics. And this is super useful. If you want to visualize anything, if you want to create dashboards or alerts, this is what we want. So many of these aggregations happen at Apache Flink. Fifth one is routing to multiple outputs. Flink routes these logs to the right destinations depending on type. So fully enriched logs goes to OpenSearch or Elasticsearch. This is used for searching purposes. The second one, aggregated metrics go to time series database like Prometheus, Timescale DB, etc. This is used for metrics, graphs, and alerting things. The third one, batch files. The batch files go to S3 or object storage. This is used for long-term archival and offline analytics or data lake. So Flink is basically the traffic controller, deciding what logs go where in what format and how often. Now we have chatted about what Flink does. We have listed out all of the tasks that it does. But why did we choose Flink for this? Well, Flink is a real-time stream processing engine. It processes data as it arrives, not after the fact. That means we can get real-time dashboards, instant alerts, continuous transformations, ability to handle millions and millions of events per second. And that makes it the perfect candidate for the distributed logging pipeline. So to summarize, Kafka stores and buffers logs, whereas Flink cleans, enriches, filters, aggregates, and routes them. Together, Kafka and Flink form the powerhouse of modern logging architectures at companies like Uber, Netflix, and Amazon. Okay, now that Flink has done its job, filtering, enriching, and aggregating logs, it's time to send those logs to their final homes, the storage backends. Yes, these are the storage backends that you see here. If you look at this diagram, you can see three main destinations after Flink: Elasticsearch, Timescale DB, and Amazon S3. Each one serves a different purpose, one for search, one for metrics, and one for long-term storage. So let's go through them one by one. The first destination is Elasticsearch. This is for fast search and querying. And if you notice this arrow right there, it is labeled as enriched logs. Now, what does that mean? These logs include useful information like service name, timestamp, log level, and that all important correlation ID that we saw earlier. Elasticsearch takes these enriched logs and builds something called as inverted index. Think of it like the index at the back of the book that you see. It helps you jump directly to the page that mentions a specific word instead of flipping through every page, searching through every page. Let's say if you want to search for word Kafka, you go at the back of the book and search for the word Kafka and in what pages was this word found. Similar to that is inverted index that Elasticsearch creates. But in this case, Elasticsearch does that job for the logs. And because of that, developers can now search logs instantly by keywords, correlation ID, or even service name. So if you want to find all logs where the word timeout appears or track one request end to end using its correlation ID, Elasticsearch can do that in milliseconds. And this is the same technology that powers tools like Kibana and OpenSearch dashboards, where you get all those rich visual charts and search bars. So, in short, Elasticsearch gives you fast search and visualization for logs. Okay, enough chit chat about Elasticsearch. Let's move on to the second one, which is Timescale DB. This is for storing metrics over time. And as you can see in this arrow right there, it is labeled as metrics and it points to Timescale DB. Now, Timescale DB is a database built on top of PostgreSQL, but optimized for time series data, data that changes over time. In this case, we are getting a lot of these logs every single second. So it becomes a time series data. Now, Timescale DB is the place where we store metrics. Metrics like error rates per minute, average request latency, success and failure ratios. These are the numbers you typically see on your Grafana dashboards too. We'll see that later on. They help you track trends and identify when something's off. For example, error rate doubled in the last 10 minutes. That's problematic, and that's how we get to know from Timescale DB. In summary, Elasticsearch helps you to find what happened, whereas Timescale DB helps you understand how your system is performing over time. Now let's move on to the third one, which is Amazon S3. This is used for long term storage and archival. Now, what does that mean? Let's understand that deeply. First, you see this third arrow from Flink labeled as Parquet that points to Amazon S3. S3 is our data lake and archive. All logs that are not needed for real time analysis get batched into hourly or daily Parquet files and stored there. Now, what is this Parquet file? Well, Apache Parquet is an open source columnar storage format. So, unlike traditional way to store data, which is based on rows, in this format we organize data based on columns. So, simply put, all the columns are saved separately. So, these Parquet files are saved in S3, and if you ever need to analyze historical data, say for compliance, capacity planning, or comparing incidents across months, these Parquet files in S3 are your gold mine, because saving these in S3 in Parquet format is very low cost and very durable storage for historical logs. So let's do a quick recap of the technologies used in this. The first one was Elasticsearch, used for fast full text search and visualization. The second is Timescale DB. This is used for storing time series metrics and enabling alerting based on the logs. The third one was Amazon S3, in which we stored the Parquet files. This was used for long term, cost efficient archival and offline analysis. Let's say you want to do some analysis on a huge chunk of data, you can do so using Amazon S3. Let's connect all of the things together now. So microservices produces logs, log agents collects and forwards them, then Kafka comes in, takes those logs and transfer it to Flink. Flink processes and enriches the logs, and finally logs are stored in Elasticsearch, Timescale DB and S3. Together, these three storage backends form the foundation of our logging system. They let you search logs instantly, monitor metrics in real time, and store everything safely for the long run. Now that we have seen how the logs are stored, let's move to the most exciting part, how developers actually use this data. So that's what we'll see in this section. This section is all about querying and dashboards, where tools like Kibana, Grafana, and Athena bring our logs and metrics to life. So if you look in the diagram, we start again from Flink at the bottom left. Flink sends three different types of data that we saw: enriched logs to Elasticsearch, metrics to Timescale DB, and Parquet files to S3. From these storage systems, developers use different visualization tools to explore and analyze everything. So let's break it down step by step what will happen next. First one is Kibana. If you look at the top of the diagram, you'll see Kibana connected to Elasticsearch. Kibana is a visualization tool that sits right on top of Elasticsearch. It lets developers search logs, build dashboards, and visualize trends. So when Flink sends enriched logs to Elasticsearch, Elasticsearch builds those inverted indices that we saw earlier. Then Kibana takes those indexed logs and gives developers a beautiful searchable interface. You can search by keyword, service name, or correlation ID. For example, if I am a developer and I want to search for debug logs for a particular user, then I can search for that. So in short, Kibana plus Elasticsearch gives us the capability of instant log searching and visualization. And it's used in a lot of different companies. The second one is Grafana. This is connected to Timescale DB. Now look into the diagram, you'll see Grafana connected to Timescale DB. Grafana is a very popular dashboarding tool, especially for time series data that changes over time like error rates or latency. It pulls these aggregated metrics from Timescale DB, and then developers can then visualize trends like spikes in error rates or increase in latency, or create beautiful time-based charts, or set up alerts. For example, send an alert if the error rate goes beyond 2% for the last 5 minutes. All those can be done inside Grafana. So Grafana and Timescale DB together are the backbone of real-time monitoring and alerting. Now comes the turn for Athena. This is connected to Amazon S3. Now, Athena is an interactive query service by AWS. It lets you run SQL queries directly on the archived logs stored in S3. We saw earlier that the archived logs were being stored in S3. Athena basically has the capability to run interactive query. Now, since Parquet format is used here, and it is compressed column-oriented format, Athena can quickly scan and query even terabytes of data. This is perfect for long-term analysis. For example, if you want to compare incident frequency over the last 6 months or generate compliance reports, this is the perfect tool for you. So with these tools, we have the capability to debug a request, spot errors, run reports, get alerts, and many more things. So let me do a final recap of our design. A client request flows through the API gateway and microservices. Now, we have these log agents that collect logs and send them to Kafka. Then Flink processes it and routes them forward. Then it reaches Elasticsearch, Timescale DB, and S3. And then finally, Kibana, Grafana, and Athena bring all of this log data into life. Kibana helps you search and visualize logs. Grafana helps you track metrics and set alerts, and Athena helps you query archived logs across long time periods. Together, these complete the end-to-end distributed logging system. Now it's time for the deep dive insights. The first deep dive I want to have is the Protobuf or Avro serialization. Lots of big words, but interesting ones. So let's start off. First of all, why do we even need serialization? If you look at this diagram, everything starts from the microservice on the left, each microservice continuously generating logs, usually in JSON format. JSON is great for readability, humans can easily understand it, but it's not efficient for machines to send or store at scale. Why? Because JSON can have multiple replications. Every single log repeats the same field names like timestamp, service, level over and over again. Lots of repetitions, as I said. So, when you have millions of such logs every single second, that's a lot of extra text being sent over the network. This means more bandwidth, higher latency, and higher storage cost. Serialization solves this. It basically means converting data into compact binary format before sending it. This binary data is much smaller and faster to transmit. So instead of sending a big text log, we send a small binary packet that represents the same information. Now, the second question arises, how we use it in our design. Let's go through the steps shown in the diagram. The first step, the microservice first produces a normal JSON log. For example, service payments, level error, timestamp 2025 925 T12. The second step is when the daemon set log agent that we saw earlier picks up this log and serializes it using either Protobuf or Avro. Now we'll understand Protobuf in just a second. Now, instead of sending the entire JSON string, the agent converts it into a compact binary representation, as you can see in the image. This binary version is much smaller in size. Now, let's talk about Protobuf or protocol buffers. Now, Protobuf was developed by Google. Think of it as a way of defining a template or blueprint for your data. Let me explain how. So let's say you have a log event template. Now this log event template includes service, level, and timestamp. So we define the schema like this. Now once this schema is defined, both the sender and receiver use it to encode and decode the data. So instead of sending the actual text, service, payments, Protobuf just sends a small tag and value. For example, field 1 equals payments in binary format. So it will send 1 instead of payments. That's just a very simplified example, but I think that should give you a good feel on what Protobuf does. So in summary, it's super compact, language independent, and works beautifully with microservice technologies like gRPC. In short, Protobuf makes data smaller, faster, and structured. Another interesting fact, it is widely used with Kafka because it stores the schema along with the data. That means even if Flink or another consumer doesn't have the schema file, it can still read the log correctly since the schema travels with the message. Now let's continue with the flow in our design. Until now, the daemon set log agent picked up the log and serialized it using Protobuf. The third step is when the binary message goes to Kafka, which stores it in topics like logs.raw. These are serialized log streams ready for consumption. The fourth step, Flink or any other consumer reads from Kafka, it uses the same schema that we saw to deserialize the logs back into the structured objects. So even though logs were stored in binary format, Flink can still understand them perfectly by decoding them with the same schema. This whole process ensures that logs move through the system efficiently with low latency, high throughput, and consistent structure. Okay, now let's move on to our second deep dive, where we'll look deeply into Apache Flink. First of all, what is Apache Flink? It is a framework for real time stream processing. It processes data as it arrives. Note that we do not process it in batches. So it processes data as it arrives and can perform transformations, aggregations, filtering, and enrichment on the fly. And that makes it super powerful. So, in short, think of Flink as a data transformer that reads from Kafka, cleans and enriches the data, and sends it to the right places. Now, once we know what Apache Flink is, a natural question arises, which is how Flink transforms our log data. For this, let's look at our diagram. Let's say Kafka receives this raw log event, which says service, payments, status 500, latency 3100, region US East 1. So the first step is Flink reads it from logs.raw. Then in the second step, Flink enriches it. That is, it adds derived fields. Earlier we had service, status, latency, and region. Now it adds status class and timestamp to it. In the third step, Flink filters out unnecessary fields, example debug logs. In the fourth step, Flink computes aggregates like service payments, window 5 minute, error rate 0.12, average latency 2800. Basically saying that error rate for the 5-minute window is 0.12 and average latency for the 5-minute window is 2800. And in the final step, that is step number 5, it sends enriched logs to OpenSearch, sends aggregated metrics to TimescaleDB, stores hourly batches to S3. Pretty clear what Apache Flink does? Now let's move on to another question. How does this metric aggregation happen? Well, Flink groups the log by time windows to calculate metrics like error rate or latency trends. Here are 3 common windowing strategies. The first one is tumbling window. Here we have fixed non-overlapping time intervals. So for example, if you want to find average latency every 10 minutes, Flink groups all logs that arrive between 12 to 12:10, 12:10 to 12:20, 12:20 to 12:30, and so on. So we will have only one average latency each for each of those windows that we see here. So for the first window, as you can see, we have 3 and 5. So the average latency in that window is 4. In the second window, we have 6, 1, 3, and 2. So the average latency is 3. Similarly, for the last window, the average latency is 2. Now there could be another windowing strategy. This is called as hopping window. Here we have fixed window size, but windows overlap because they start at regular hops. Example, a 10-minute window with a 5-minute hop means, in this case as you can see, the first window is 12 to 12:10. The second window is 12:05 to 12:15. You see the overlap there? From 12:05 to 12:10. Similarly, we can have the third window from 12:10 to 12:20. Here again, the overlap between second and third window is from 12:10 to 12:15. So let's say a single log at 12:12 contributes to 2 windows, the second and the third one. And this is useful for rolling averages or moving trends. Now let's talk about the third type of strategy, which is sliding window. This is like a continuously moving window. It updates with every new event. Example, if you want the latest error rate over the past 10 minutes, the window slides by every incoming log. Flink recomputes metrics dynamically as new data arrives. This is used for real-time monitoring dashboards. Let's take a look at our example. So the first one came just after 12. So the first average latency that we see here is 3. Then when 5 came in, the average latency went to 4 for the last 10 minutes. Now, just after 12:10, 6 came up. So the average latency for the last 10 minutes would be 6 plus 5 divided by 2, which is 5.5. And we keep on doing it. And that is why we use it for real-time monitoring dashboards. Because it's like continuously moving window. It updates with every new event. That's a wrap for the Apache Flink. Hope you learned a lot here. And that's a wrap for our deep dive inside too.